Okie dokie, we're going to get started. Thanks for coming. We have internal speaker today, who is Silke, who's a third-year PhD student. You should know who she is, so if you don't, shame on you. And today she's going to talk about AGB outflows as part of her PhD thesis. So Silke, over to you.
Yes, thank you for introducing me. So indeed, I thought it's my third year. There weren't many slots filled, so I might as well step in. So I'll tell you a little bit about my PhD indeed today. And more specifically, I'll guide you through the route that we are trying to build towards 3D chemical models of AGB outflows. So I listed here my collaborations. It's a lot of people from KU Leuven, but also still I work a lot with Marie, who was here before. And we also work together with Lionel CS from the ULB and also with JN and a difficult last name from a University College in London, who are trying to help us with this project. So let me first quickly remind you what again are AGB stars for the ones that might have forgotten or for who it's far in their minds. So AGB stars are evolved low and intermediate mass stars, so they are located there in the upper right part of the HR diagram. And their most interesting characteristic is actually that they experience a large stellar wind. And we believe that this wind is dust-driven, which means that surface pulsations levitate material from the atmosphere of the wind and then launch it into interstellar space. And there the conditions are ideal actually for dust grains to grow. And the dust grains can absorb the infrared radiation from the AGB star, and that's how in total there is a stellar wind launched. And because of the stellar wind, so there's a mass loss, we get an outflow, and this creates a large circumstellar envelope, as we call it, or also CSE in short. So I here very schematically try to draw it. But what's very interesting about these outflows is that their density is high, relatively speaking, but the temperatures are already low, and this is then ideal for a lot of molecules to grow and also for rich chemistry to be there. And observers have observed almost over 100 molecules already in these CSEs of AGB stars, and also a lot of dust species. And also this dust is of course important, as I was mentioning, for launching the wind itself. Now, with more high resolution observations, people have also seen that these AGB outflows, long has been thought that these were nicely spherically symmetric, but now we see that there's also some structure present in them. So here I show you some of the AGB sources from the Atomium project of Leen. And you can see the red and the blue parts, that there is structure in there. We have some arcs that we see, some spiral-like things, also a bit of bipolarity, for example, here in Hydra. And the hypothesis currently is that these structures are due to binary interaction. So we think there is a binary companion hidden in the outflow, and that it can shape the outflow in these structures. Of course, this brings along some challenges, because of course, when there is a binary companion present, the theory is different than we might have thought before, because in the past, people have derived the wind properties and also other properties of AGB stars, assuming they are single. But now we assume they're not anymore, so this means that, for example, the mass loss rates that we have calculated from observations, or also the expansion velocities of the wind itself, the chemistry that's happening, all those things might have changed with the view that there might be companions present. And in order to check this, or to try to model, find out what's happening, we're trying to model these things in 3D, because we need this 3D thing, of course, because we have the structure. And as you probably all know, modeling things in 3D, whatever it might be, it's a challenge, it's hard, it takes a lot of computation time, and sometimes it's even unfeasible. So we're trying to overcome these challenges. Now, so the aim of the research, the bigger aim, is that we want to model these things, but of course for the modeling we need different ingredients, as I called it here. So first of all, we have these observations now, but what do we see in the observations? It's emission from certain species. So if we want to model the emissions from these species, we of course need to model the chemistry, so that we get abundances, and then we can later process this to get emissions. But also the chemistry depends heavily on the physical background, so what's happening with the densities and the temperature. To model that correctly, we of course need accurate hydrodynamics, so that we get densities and temperature, so that from that we can know what the chemistry will do, and in the next step again convert that to observations. Now, to link these three blocks, we also need radiative transfer and a bit of thermodynamics to have it as a whole in the model. Yeah, of course, these are individually, these few building blocks are already computationally intensive, and if we also want to couple them, it takes a lot of time. So therefore, in a first approach, we are exploring the different building blocks separately. What we also want to include in these models is, for example, proper dust, but dust growth and how this dust reacts with the radiation, because as I mentioned, the launching of the wind itself is mainly due to the dust. We also need to implement proper cooling because of all types of different mechanisms. And then as lastly, we also want to include these pulsations that I mentioned because they launch the wind in the end. And for now, we have some approximate prescriptions for this, but we hope in the end to have really a full model. And as I mentioned, we want to do this in 3D. So what are we doing currently? So first of all, for the hydrodynamics, we're using the SPH hydro code Phantom. And in this code, for example, Lionel Sies at ULB has implemented the wind physics, and recently Mats added to this array tracer. So we already have some notion of radiation in there, so that the wind launching mechanism is already improving very much. And on the other hand, for the radiative transfer modeling itself, we often use the Magritte code, which Frederik built during his PhD here. And from that, we can already compare roughly two observations. But the thing that I'm now working on mostly is the chemistry part, because that's still lacking mainly. But first, let us have a quick look at the hydrodynamic research. We're not the only ones doing this. There are also many other people who have modeled these HB stars with their outflow, where they include a companion. And from these things, from these models, we already get some interesting results from which we can really start from and work on further. So for example, these are some figures that I published in my first paper. So what you see here in the very center, you see small dots, and those are the HB star and its companion close together, and we're looking at the density when you look at the orbital plane, so face on, as they call it. And the main thing that I want you to take away from this is that if we vary some of the parameters, for example, the mass of the companion, but also the velocity of the outflow and the distance between the HB star and its companion, you see that we get different kinds of spiral structures. So when the companion is of low mass, we see that we have barely, or we see the spiral barely, it's only, yeah, even certainly on the presentation, you almost never not see the spiral. But then when we have a higher mass companion, you clearly see a distinct spiral structure in the outflow. But when we change the velocity, for example, we see that the spiral changes shape a little bit. And if we also put the two components closer together, we sometimes get irregular spirals. Irregular spirals. We can also turn around these models with 90 degrees, so that we look into the meridional plane, as it's called, so edge on the system. And there we see that there's also a lot of difference between the models depending on the input parameters. So another interesting result here, what we see is that it's really a 3D structure. So for example, the model here with the arcs, these arcs are like the cross sections of the spirals, so we know that these are 3D spirals. Another interesting thing is that depending on the parameters, we see that the outflow is like compressed to the orbital towards the orbital plane, and this maybe is an indication of how, for example, circumbinary disks around post-HB stars might form. So that's also a link we're trying to solve here. Now, if you want to know more about what parameter causes what, I guide you to my paper there, and also to Jolene's paper, because we have been doing this research together. Then more recently, also in a paper that Jolene is preparing, because we have now more accurate cooling in the models, we see that around the companion there are some accretion disks forming. So here we are again looking at the orbital plane, and I show you a zoom in of the HB star is slightly on the left, you can still see it, but then here this dot, that's the companion, but the higher density region that you see, this is the beginning of forming an accretion disk, and we can see this from the arrows, which indicate the direction of the velocity. We can also again tilt this model, and then we see even that this accretion disk is slightly flared, and that's already an interesting result. And Jolene will be further analyzing these things, so keep up to date for this. So as we see, the hydrodynamics gives us already very interesting results, but of course we want to model the chemistry, as I told you, to in the end be able to compare to the observations. As a first step to go into the chemistry, I am working first with one-dimensional models, which have been used already for trying to model some observed HB stars. But in this case, we actually want to find out all these spiral structures that we now see in the hydrodynamics, is the chemistry actually sensitive to this? So if we just go radially outwards in the outflow, if we encounter a higher bump, or like this spiral bump, and the density and the temperature are higher there, the question is, does the chemistry really care? And that's why I performed a one-dimensional chemistry sensitivity study. And this paper, I got an email earlier this week, is now really published in MNRAS, so go check it out. And the question that I'm asking in the paper is, how sensitive is the chemistry to the physics around HB star? So with chemistry, I mean, I'm looking at the abundances and also envelope sizes of parent species, which I will explain in a moment. And for the physics, we change basically the outflow density of the wind and also the temperature profile throughout the wind. So this is a screenshot of the paper, so go check it out for more details. So the model that I'm using here, so it's a one-dimensional model. So yeah, we just are looking radially outwards in the wind. We assume there is some HB star. We set the radius of the HB star to about 1 AU, and we assume that from this point on, a smooth outflow is launched. And the outflow density and the temperature are parameterized by these two formula. But we don't care about the beginning of the wind because a lot of, not unsure things happen, but at some point the wind becomes steady, we know this, and that's where we start our model. And it will be about around 10 AU. And there we actually set some parent species. So for about, you can see the list here, for about 10 species, depending on the chemistry type, we set an initial abundance, and all the rest of the abundances is put to 0, and then we let the model do its thing. So we let the chemistry calculate. But now, how is this chemistry driven? It is because outside of the HB outflow, there's still the interstellar medium, and there is a lot of UV radiation present. So it's actually the UV radiation that will penetrate the wind from the outside and will cause the parent species to photodissociate. And the daughter species that are created in the process will start to react with each other, and a whole bunch of chemistry happens. So that's more or less in this region. And for these models, I only need to take into account the gas phase chemistry, because as I mentioned, the dust is mainly important for launching the winds. So this is the argument for it, that we only use gas for up until now. And to give a bit of details about the chemical model, it's a quite large chemical network that we use from the UMIS database. It contains about 500 chemical species, and these are all connected by more than 6,000 reactions. And so in my paper, what did I do? I did kind of a parameter study where I varied the inputs. So I varied the mass loss rate and the expansion velocity. And in the end, this means that I'm varying the density profile. And also I varied the temperature profile by choosing different values for the stellar temperature and this little epsilon exponent, which determines the profile, the steepness of the temperature. I also look at two types of HB stars. So we have the carbon-rich and oxygen-rich type. So it basically means that they have a different kind of chemistry that is happening. And that's interesting to look at. So a little bit more about how this chemistry is calculated, because I just said you let the model run. But what does it do? It solves ordinary differential equations. And each of these equations tracks the amount of species that is present there in function of time. And basically, we can say that the amount of a certain species is just the difference between how much is produced and how much is destructed by the other chemicals present. And every of this chemical reaction is set by a certain coefficient, a rate coefficient. And for two body reactions, which is a large chunk of the network, this is mainly given by the Arrhenius law, which I show here. And as you can see, it's parameterized by 3 parameters. So by alpha, which sort of sets the probability. Then we have beta, which gives the whole thing a temperature dependence. And then there is still gamma, which also makes the reaction dependent on the temperature, but more in the sense that there is an energy barrier present when this gamma is larger than 1. Here I show you schematically how my grid looks. So in total, I have about 34,000 models that I try to analyze. Yeah, of course, group together. And I use about 50 different setups for the density, as you see here in the grid. And people from observations have found that there is a linear dependence between the mass loss rate and the expansion velocity, and that's why not the whole grid is filled here. I take into account this linear dependence. And then for temperature profile, you see that it's mainly the exponent that sets how steep the profile is. And we can actually more or less distinguish between the hotter profiles, or where the wind stays hotter throughout the outflow, and then where the wind cools down. And for lifting the degeneracy of showing my models for the what is coming now for my presentation, I used a color code which just gives this reference temperature that I indicated here in pink. So as you will see later, red color will mean it's not a very steep profile, so the outflow stays quite warm. And then when I go to the blue, the outflow will cool down much harder throughout the outflow. So let us now look at some results. So what is the effect of changing the density of the outflow? So what I show here is the abundance profile of two species. So we have C2H2, which is a parent species, and I also show its daughter, C2H. And so we look radially outwards in the wind, and we have the abundance of the species on the y-axis. And the color is, as I just mentioned, this reference temperature so that we know which models are shown. So what do we see here? We see that for the parent species, so C2H2, it's quite constant up until a certain radius, and there it drops drastically. And this is because the UV radiation, as I mentioned, is coming from the outside, is able to penetrate the wind, and at some point destroy the C2H. And at that point, so the C2H2 gets photodissociated into its daughter species, and that's why, ooh, that was too quick. And that's why you can see the bump here at the same location. So at the point that the parent is destroyed, the daughter is created, and then also a bit later in the outflow, the daughter is also destroyed because of the photodissociation. So if you now lower the density, I have a few examples, you can see that the location where the parent is destroyed by photodissociation shifts closer to the HB star. And also the peak of the daughter species shifts along with that. And this is because, of course, when the density is lower, it makes sense that the UV photons can penetrate deeper into the outflow. And another thing that we notice when we go to lower densities is that the abundance profiles become much more temperature dependent. So as you can see here, there is a much larger spread actually on where the species are destroyed. So that's an effect that we will look at now. How come are these profiles also very temperature dependent? So as I mentioned, we have the parent species. Here I show the parent species, and it's photodissociated into its daughter. But it can also be reformed again. So by adding molecular hydrogen to the daughter species, the parent can be recreated. But this can only be when the temperatures are high enough so that the reaction can overcome its energy barrier. Because for this specific reaction, if you look again at the Arrhenius law, I don't know by heart what the numbers is, but the gamma will be about some 1000 Kelvin. So we need high enough temperatures for the reaction back to the parent will proceed. So if we look at the abundance profile, what happens? For the blue models, these are the models where the outflow is cooling down quickly. The parent gets destroyed, but the temperatures are not high enough, so the parent is not recreated again. Hence, it only can exist to shorter radii of the HB star. But now when the outflows are hotter, so for the red models, the parent species photodissociated actually at the same location as the blue models, becomes the daughter, but the daughter, there's enough, where the temperatures are high enough so that the daughter can be recreated into the parent. But of course, at some point, the temperatures have dropped also there in the outflow, and the parent cannot be recreated again. So it just stays destroyed, and it's photodissociated again. So that's why this is what I found why most of these abundance profiles become temperature dependent because of these energy barriers. And of course, it's not only for these species, but very often when species attach a molecular hydrogen, they have to overcome an energy barrier. However, in the chemical network, not all of the chemical reactions depend on such an energy barrier, but still their abundance profiles are dependent on the temperature. So I asked myself the question, how does this happen? And it is actually because they are inheriting profiles of their reactants. So for example, I here show you the abundance profile of OH. And the typical thing you see here, the pattern of its abundance profile, is because of what I just explained. So we have water. Water can photodissociate to OH, but water can also be reformed with OH and then adding molecular hydrogen to it, and including an energy barrier. So that's again why the bluer models are short to the AGB star than the red models. Now, OH is a very important reactant species in oxygen-rich chemistry. And as we look at some of the parent species of oxygen-rich outflows, we see, for example, that the CO2 and SO, they also have a temperature dependence in their abundance profile, but not because the specific reactions that happen are dependent on temperature. But what happens is, for example, the CO2 photodissociates into CO, but if we add OH to CO, we can again reform CO2, but now because OH has this temperature-dependent density abundance profile, also CO2 will become dependent on temperature, and that's what you see here. So shorter towards the AGB star, the blue models reach a higher abundance because there we have more OH available. And the same holds for SO. So in this way, also the temperature dependence can propagate through the chemical network, and this actually means that probably the abundances of all species still depend on the temperature. So temperature is a very important parameter to take into account in the chemical models. Another part that I did in this paper is looking at uncertainties. And I did this by a sensitivity analysis, because what is important actually, if we observe these AGB stars with their outflow, people of course retract from that some of the typical properties, for example, the expansion velocity and the mass loss rate that I mentioned before. These are from observations also gained. But the observations, we just observe spectral lines mainly, and to get these properties or the specific numbers for the AGB stars, a lot of modeling comes in between. For example, to get the expansion velocity, we use the width of the lines, but luckily this is a quite accurate method to do it, so the width of the lines can be determined quite accurate, so there isn't too large of an uncertainty on the expansion velocity. However, the mass loss rate, and also to get some notion of the temperature profile throughout the outflow, to know numbers for these parameters, we need to do some radiative transfer modeling. And this is an expensive thing, and people mostly do it in one dimension, which seems fine as long as the AGB outflows seem spherically symmetric. But we know that's not the case, and so this means that a lot of assumptions go into the radiative transfer modeling to get these parameters. And hence this means that on the values of mass loss rates, for example, there are typically large uncertainties on there. Some papers state it can be a factor of 2, but also larger factors. However, this is a thing that people not very often communicate, because the uncertainty is just uncertain on its own. So it doesn't really matter if you give a very large uncertainty or a small uncertainty if you don't know it. But the most important thing is, from all of these observation things, we also retrieve some abundances for specific species. But if already parameters like the mass loss rate have large uncertainties, also the abundances will have large uncertainties, but these are mainly unknown. And this is a gap I try to bridge here with this analysis. So how did I do this? For the parent species, I did this by calculating the envelope size, which is generally given by the e-folding radius. And this e-folding radius is defined as the radius at which the initial abundance has dropped a factor of e. So the pink lines that I show here. And thus we get a certain radius for this value. But of course, in this case, as I showed you before, my abundance profiles are dependent on temperature, or can also be dependent on density. Depends how which plot I show, basically. So there's also a range on this e-folding radius, or on the envelope size, and this is a little bit the range that I'm trying to calculate. In this case, that then gives a notion of the uncertainty on this value. So for example, the plot that I show here, we have this envelope size of e-folding radius on the y-axis, and then the x-axis together with the color bar indicates the density of the outflow. So for specific expansion velocities, for example, for 10 kilometers per second, I calculated models with different mass loss rates. And as you can see, if you have a lower mass loss rate, the e-folding or the envelope size is smaller, and if the mass loss rate is higher, we have a bigger envelope. And what can we do now, or hopefully people will do now, if they observe a source and they estimated the parameters of this outflow to be a mass loss rate about 10 to the -6 and an expansion velocity of about 15 kilometers per second, they can say that their observations sort of coincide with a certain dot in this plot. And then, because mainly their uncertainty is unknown, or even if they know the uncertainty, that will even be better, but let's say they estimate an uncertainty of a factor 2 on their observed values, my theoretical models indicate that then the size of the envelope also varies with that. So here the black bar that I added indicates how large uncertainty can be on the value of the envelope size of this specific species, of course. If we assume a larger uncertainty, for example, a factor 5, this uncertainty becomes larger, as you see here. So in this way, we are trying to estimate, do an estimated guess of the quantization of the uncertainties on the abundances. And I did this for multiple parent species. This is a very filled plot, but I don't expect you to read it in detail. The main point to take away here, so depending on the mass loss rate, we see that there is a big change, or a big change in envelope size, so quite large uncertainties. I did a similar process with the temperature profile, so now the color indicates this epsilon exponent that indicates the steepness of the temperature profile. And as you see here, for some species, for example here again C2H2, uncertainties can be quite large, but from other species, for example SiC2, that's also a parent species in oxygen-rich stars, we see that the temperature has less effect. So from this we can conclude that it's mainly the uncertainty on the mass loss rate that we retrieve from observations that will have the largest uncertainty on the abundance profile. So this brings me to a temporary conclusion of my seminar so far. So by the work that I've done, we can mainly state that indeed the physics, changing the physics has an important impact on the chemistry, so we should go to 3D and not stay within 1D for our, for making our hydrodynamical models better. Now, how will we do this? So the one-dimensional chemical models, they don't take too much time, so that's already good. But if we want to have a hydrodynamical model and include those chemical models into that, the hydrodynamical model takes already a lot of time on its own, and if it then also had to add the calculation time of the chemistry, this will just be too much, and then it's not feasible to run a big grid of models. So we need to come up with a smarter way or another way of calculating the chemistry. So quickly to remind, what is a chemical model? Basically, we have an input, we have some physical parameters like the density, temperature, and some radiation field, and then we also have the abundances. We put this through our model, and what we aim for is to have an update on the state of the abundances. The physics can stay constant, that's what we're fine with. And classically, this is done by solving the ordinary differential equations that I showed so far. Now, what we aim to do is do it another way, using an emulator that uses neural networks, and with the technique of machine learning, we are trying to do the same, and that's why it's called an emulator, because we're not literally calculating these things, but emulating. So the idea is the same. We have an input, and also an input for the abundance. We want to keep the physics constant, but we want to have an evolution of the chemistry. This is not the new idea, it's not that we invented this. People have already researched this, and they have found that indeed, by using an emulator with these neural networks, we can really have an immense speed up, about a factor of 10 to the power 5, they state here in the paper. And this would mean if we can build such a chemical emulator, and if we connect that back to our hydrodynamical models, this would mean that actually the hydrodynamical models would not take significant time longer than just the hydrodynamics. So that would be just perfect. Now, by researching this, so we aim to build such an emulator, and we came up with the name Maes, which stands for Machine Learning Approach to Chemistry Emulation, which is, in my opinion, quite a good acronym. But a little anecdote about this, the name came to existence by inspiration of my own last name, which is Maes, but I thought in international environments people might pronounce it as Maes, and hence it fitted with the acronym, so that was nice. But now, what will Maes be, because it's still very much under construction? But we aim to, at first, use a fully connected autoencoder to reduce the parameter space of our abundances. So what do we do, or what do we plan to do? We have our chemical abundances, vector n, and we want to reduce the dimensionality using an encoder built of neural networks. And then we have a reduced version of this called Z. And the clue is actually that we do not aim for this Z vector to be still physically interpretable. So if it's just some mathematical thing that works, we're fine with that. Of course, as I just mentioned, we cannot interpret this, so we also need to encode this again, or decode this, I mean, also by another neural network. Again, this is not a new idea. People have done this before me and have found that this works up until a certain amount of elements in the n vector. And for example, the paper by Holtship et al., they did this for a vector that was about 30 elements, so an abundance set of 30 species. As I mentioned, we have 500, so we aim to increase this with a lot, but hopefully it works. Now, if we would have this autoencoder, that would already be great, but as you can see, we are not updating the abundances yet, or the chemistry yet, and that's of course the clue. We want to know how abundances evolve. So in this latent space, as it's called, so with the Z vector, we aim to do the update of the abundances. And for this, we will try to use the technique of neural ODEs. It's not the classical neural networks, as most people maybe know, but we aim for a certain differentiable function in the latent space that is, again, trained. And what is the benefit of using neural ODEs is, since it's differentiable, you're not bound to a certain discrete time step. Because of course, if we would put here just a default neural network and we train it with our chemistry data set that always contains the same time step, we are restricting our models very much. So we want this to be differentiable. And a paper about neural ODEs, I found they have a plot that sort of gives the feeling what they mean. So in a classical way, what the axis means doesn't really matter too much, but the main thing is that there is a discrete step every time that you go through. And then the colored arrows more or less indicate the results that you can trace. And as you can see, these colored arrows do not really fill this space. However, if we go to the technique of neural ODEs, our steps are not discrete anymore, and they can vary depending on what we want. And this way, they can really trace the whole parameter space. Or in our case, this would be the whole evolution of chemistry. So that's why we have chosen this technique. To be honest, we are still in the beginning process, so we hope this will work out. But yeah. So a little bit more details about the neural ODEs. So we choose a certain function, j, which depends on our encoded abundances and also the physical parameters, which we just here put as p. And we can parameterize this function as a polynomial where we have a few matrices. We can choose how much we want, but let's stick to these three. And each of these matrices is a separate neural network that can be trained in the normal ways neural networks are trained, I mean. So this is a little bit what is behind the technique. So this gives us the following scheme for Maes. So we will encode our abundances. We will then, in the latent space, try to use this neural ODE technique. We will still feed the physical input parameters and some time step, of course, into these neural ODEs so that it knows how it should evolve, and then hopefully we get a nice result in the latent space, which we cannot really interpret, but that's fine as long as we can decode it again to something we know. We're happy. So we will try to train this whole thing as a whole, and so not separately the encoder, the autoencoder apart, because of course the neural ODEs, depending on what they need, they can also set the size of the latent space. So we don't really care about the details, let's say, as long as the thing works as a whole and can emulate the chemistry in a quick enough way, we're happy. We would be happy with the results. So this means, imagine we already have Maes. how will we now use this? We will then combine the hydrodynamical models with the chemistry. We will do this in the following way. So at some hydrodynamical time step, Phantom does its thing, and it calculates the density, the temperature, and some radiation fields. We know the abundances. We will give these values to Maes. Maes will then be able to update the chemical parameters, so the abundances, give it back to Phantom, and in that kind of loop, we hope that we can, in the end, have then a model that contains hydro as well as chemistry. So this brings me to the conclusions of my seminar. So what we've learned so far is we assume AGB stars have companions and that they are influencing the outflow, and that the result is some complex morphologies, and we want to know what's happening in those. To do that, we need 3D modeling because 1D is not sufficient anymore. And the 3D modeling depends on the different building blocks, namely hydrodynamics, chemistry, and radiative transfer. And we need these 3 big building blocks in order to really compare to the observations. For the hydrodynamics alone in 3D, we already get some good first results, and this is very interesting. And now we can just gradually add more physics to it, so we can really disentangle all the effects. And also the 1D chemistry gives us a little bit the same notion of it. We now know why abundances become temperature dependent. I found that this is mainly due to the energy barriers. And also we need to still take care about the uncertainties that it can bring along. But as a whole project, we also know more about chemistry now. And so we're ready to couple these two. And as I just explained, I will be trying to build Maes in the rest of my PhD. And hopefully then in the end we can couple it to hydrodynamics, and we can come one step closer again to really finding out what's happening in AGB stars. Thank you very much.
Thank you, Silke Maes, for such an excellent talk and keeping to time. Questions? Andrew, you'll make me run.
Hi, Silke. Thanks for the nice talk. 2 questions, if I may. One more general, one more technical. A general one, you mentioned pulsations as a driving mechanism behind the outflows. And you said you, at the moment, take that into account in some approximate way, but you would like to have a bit more physics in it. Could you enlighten me on both of those aspects?
So on the fact that currently we're not having pulsations in our models, we just set some density that is high enough for the dust to be, it's not really dust growing yet, but to have some dust to be there. So in that sense, we can already launch an outflow. But what would be nice if also the pulsations would be taken into account, so then our wind launching in Phantom, will be periodic, and hopefully, so at some point the amount of wind that is launched will be a little bit more, and depending on that, that should be then coupled to how much opacity is there from the dust, and that would give a clear view on the whole outflow. Because also these pulsations, they're very important for the dust growth and the whole launch, but because they're periodical, maybe they can also be visibly in the outflow itself, so create some higher density shells.
Yeah, would you expect some shocks to actually occur in the outflow because of that?
Sorry?
If you include a more physical model when it's periodic, would you expect some shocks to be observed in the outflow?
Also now the spiral structures that we see already, they are also already shocks depending on how large difference is in density. So it will change a bit the outflow,
Okay, thanks. And a more technical question. So you spoke a lot about the importance of quantifying uncertainties in a proper way. And now with your Maes framework, there will be an iteration between hydro and emulation of the chemistry. And as you said, emulator is called like that for the reason. It can only emulate, it will never be accurate. How do you plan to propagate the uncertainties through your latent space?
Well, that's indeed a difficult question, and I'm looking at Frederik. He's looking into that. No, the thing is, I talked about the uncertainties. Indeed, that was something that fitted together with that one project actually about studying the parameter space. But indeed, for the combination of our hydro and our chemistry, then with these neural networks, it is very hard to propagate uncertainties. And in a first step, we will not care like everyone does. But in a later step, there are some statistical approaches, and also in the whole world of machine learning, people are working on this, how they can do it. But to be honest, I don't know the details. But I refer to Frederik if you want to know more about this. He's working on that for Margriet. So, but yeah, it's a difficult thing.
Any other questions?
Thank you for the talk. Like, what are the boundary conditions of your simulation?
We are using SPH, so particle code, and hence we don't really need to take care of boundary conditions as you guys of Ammervac should. But yeah, more the larger meaning of boundary conditions. We have this HB star, which we just assume as some sync particle without too much extra physics on it, and then we just still launch a constant amount of particles, then the SPH particles that represent the outflow, and then we just let gravity and hydrodynamics do its thing on these discrete particles.
Okay. One more, maybe I'm getting this wrong. So in one of the daughter and the parent species pictures that you showed, I suppose the peak of the, like, they almost peak at the same place, right? Like the daughter and the parent. Shouldn't like the peak of the daughter be where this drops down because of, I think?
So you mean that the peak should be just slightly more outside? I think the thing is, these are also logarithmic scales. So as soon as the parent species just drops like a little amount, in the higher things, it's already a lot for the parent species to be created. So when it starts to be created, it's like 10 to the minus 9 amount, some units, compared to 10 to the minus 4. So that's why it's at
probably
the same
like
location.
10 or 1%. It's
so it's a logarithmic scale, which is a bit misleading sometimes.
Okay, thank you.
I will pass the mic over to Alex.
Hi, sorry if I missed it, maybe you said, but for the SPH simulations that you do, did you do a set or a couple where you put in something like an additional Silke Maes to emulate a binary companion?
Yeah, so it's on this Zoom, you can see it a little bit, so wait, no, it's not too clear, but where I drew the box, there is like the HB sync particle, but in the zooming you just see here the little dots, so we put an extra sync particle as a companion, of course. Okay. And they only interact like binary-wise, they have an orbit, and depending on which mass loss prescription we use, the wind doesn't really feel the HB star itself to be able to be launched, but that's something Mats took care of. So now also the wind particles feel the HB star, but because there's now some radiation, they can really launch. But there is a companion sync particle also,
Okay, cool. I thought I remembered a plot like this. So where I was going to go with this is, is there any like plans or interest in doing these kinds of stuff, like, but instead of a binary companion perturbing the winds that are happening anyway, something more like a stripping scenario? Or is that just like a big step up where you've now got a much more complicated source particle?
So for example, that the companion would strip away the envelope and these kind of things.
Like that, like a more interactive interaction.
That's indeed not what we are doing. We're trying to keep the thing whole. But I know research groups in Australia that are also working on finding a little bit of link between HB stars and post-HB stars and binary things, and also common envelope scenarios. They use, for example, this phantom code also to do stripping of the envelope and merging and everything. But we are trying to keep the things separate and just see how we get spiral structures.
So your emulation code, though, once it's up and working, that could be easily integrated into such simulations as well, right?
Yeah, so that's actually what we aim for. We are now testing this on the framework of HB outflows, but hopefully, if in other type of physical environments, like also protoplanetary disks or maybe dark clouds, if our architecture works, like this bow tie thing I showed, that works, hopefully people with other chemical networks can just train with their own data and don't need to take care of optimizing the architecture. So that's indeed the aim, that it's transferable in an easy way to other regions.
That's a really cool capability to add. Thanks.
We hope.
Yeah, question from Pablo.
Hey, thanks for the talk. I'm curious, so you have this time-dependent model for the chemical species, but would it be a very crappy assumption to assume chemical equilibrium at a given temperature and density?
Yeah, in this case, that won't work because our outflow is moving. So that's, yeah, the temperature and the density throughout the outflow, they're not constant, so that's why we will never reach chemical equilibrium in this environment. So we need, yeah. But in our emulation project that we're doing, we will keep indeed the temperature and the temperature and the density constant, and let that evolution be done by the hydro.
Okay, so the timescales to reach chemical equilibrium in here are longer than the timescales connected to the outflow.
Yeah, for sure.
Okay, thanks.
Why didn't you ask when Andrew had his hand up?
Going back to your autoencoder, I might have missed it, but are you using the latent space to go back to move to the next layer, or are you actually feeding the result of the decoder afterwards?
Wait, so in the latent space, this image?
Yeah, exactly. So which part are you actually using then to propagate back to your...
yeah, so it's really, we get the abundances from the hydro, we push this through the whole thing, and then, of course, the decoded version we will give back to the hydrodynamical code.
And is there a reason why you then use the decoded version, or what is like the benefit of here using the neural ODEs in the middle?
Yeah, so the neural ODEs is to do the time evolution, but we can also try to ignore or to not use an autoencoder, and we can just use neural ODEs maybe on the full parameter space, which is 500 input species already. We've thought about that, and maybe we can do a try about it. It might give equal results, but yeah, just by I'm losing the word, but it feels like it will work better when you have like a smaller parameter space that we can use to do the ODEs. And also, this is an argument for this is that in chemistry, all the things are connected, and there are a lot of, or like only a few species that are very abundant throughout the outflow, and there are many species that are not that abundant, but they do make a difference in the whole network. But that's why we think autoencoding might work in this case, because people in the past have also tried to reduce chemical networks just by leaving out the species that don't really matter. But of course, you're leaving out some important information still, so that's why we try to do this approach. And we will try to do it with the autoencoder, but if it doesn't work, we'll just push the whole thing through. As long as it's quick and it works, we're actually happy.
Okay, thank you.
Okay, let's call it quits, and thanks Silke, and congratulate her on her accepted published paper as of today. So thank you.
Thank you.